Hello everyone! I'm happy to tell you that by the end of this episode, you will build your own neural network that will be able to recognize images of clothes. For this task, we will use a dataset called Fashion MNIST. It contains 70,000 images of various types of clothing, such as t-shirts, pants, shoes, bags, sweaters, coats, sneakers, and so on. Any machine learning specialist begins his training with this dataset. It is the so-called standard for training specialists. Let's remember that neural networks consist of several layers. The data, in our case images, is supplied to the input layer. Then this data passes through several layers of neurons. During this process, they are assigned certain weights. And then we have an output layer that should give answers. In our case, the output layer will tell us what is shown in the image. In terms of machine learning, this task relates to classification problems. An image is supplied to the input layer of our neural network, and the output layer determines what class of clothes this image belongs to, whether it be a coat, shoes, t-shirt, or some other item of clothing. There are 10 such classes in this set. This dataset is open, and it can be freely downloaded and used to create our neural network. It was created by the Zalando company located in Berlin, and this set includes 70,000 different images of clothes. In one of the previous lectures on deep learning, we mentioned that neural networks, in order to be well trained, need as much data as possible. Therefore, 70,000 images in principle is a good number. You can download this dataset on the GitHub or Kaggle websites. We mentioned in previous lectures that when we train our models, we divide our dataset into two parts, the training sample and the test sample. And therefore, this set is also divided into two parts. The first part, consisting of 60,000 images, will be used for training, and the second part of 10,000 images will be used for testing, in order to understand how well our model was trained. This dataset contains two files. The first file with images and the second file with class labels, that is, with the correct answers. All images are 28 by 28 pixels in size and are executed in shades of gray. And the gray intensity in each pixel varies on a scale from 0 to 255, where 0 is a completely white pixel and 255 is a strong gray color. And since these pictures are so simple, that is only 28 by 28 pixels and in the shades of gray, this allows you to work with them and build neural networks even if your computer is not too powerful. So we already mentioned that in the Fashion MNIST dataset there are 10 classes of clothing items. Here you can see them on the screen. They are numbered from 0 to 9. And accordingly, when we submit this or that image to our neural network, we will be given the class number to which it belongs. 0 if it's a t-shirt, 5 if it is shoes, and so on. So what kind of input data will be fed into our neural network? As we already said, firstly 28 by 28 pixels. If you multiply it together, it's 784 pixels. And secondly, it is the intensity of the shades of gray in each pixel. The intensity will vary from 0 to 255. We understand, right, that the computer perceives all the information in numerical terms, which is why our neural network will perceive each image as a set of 784 pixels, and each pixel will have a specific number from 0 to 255, depending on the intensity of the shades of gray. Alright then, let's move on. The architecture of our neural network will be very simple. It will consist of only three layers: the input layer, one hidden layer, and the output layer. The input layer will only transform our two-dimensional images into one-dimensional array. The next layer will consist of 128 neurons, and this number can actually be changed. For example, you can make 512 or 800, and the output layer will consist of 10 neurons, because we have 10 different classes of clothes. We are going to use a dense neural network, which means that all neurons of the current layer will be connected to all neurons of the previous layer. Each of the 128 neurons of the main layer will receive the values of all 784 pixels of the image. And each of the 10 neurons in the output layer will give us the probability that this image represents the given class of clothing. The probability will be reflected in the range from 0 to 1. Let's remember how a neural network can make such predictions and how everything works. We will use such concepts as weights, backpropagation, and epochs. First, like a human neuron, the task of an artificial neuron is to obtain information, process it in a certain way, and pass it on to the next neuron. And the connections of such neurons in artificial intelligence that receive input data, process it, and then provide the output data Such structures are called neural networks. So we already mentioned that each neuron receives an image in the format of 784 pixels, and each pixel has a numerical value, depending on the color intensity. That is, roughly speaking, each neuron receives a specific array or combination of numerical information. Then, at first, each neuron or node is given some kind of random weight, that is significance, or how much the value of the neuron corresponds to one or another image, and this weight is randomly distributed. I want to stress again that in the first stage, this weight is just random. After that, when this value is transferred to the output layer, because we actually know what is shown in the picture, because we have answers to each picture, we say to a neural network whether the prediction was true or false. So if the network predicts it correctly, then the weight of this value, or this connection between neurons in different layers, increases. And if our model made a false prediction, we reduce the weight. And this is called backpropagation. That is, we send information back to the neural layers and say either to increase or decrease the weight, depending on whether the prediction was made correctly or not. And this movement towards changing weights occurs constantly back and forth during the training. When the entire dataset, that is all images, goes through this procedure, it is called one epoch. And during the training of neural networks, several epochs are usually used, for example 10 or even 100. That is, the same images are run 100 times through all layers, each time changing the weights of neurons and making them more accurate, thereby reducing the prediction error. So let's see how you can create and train such neural network in Keras and TensorFlow. These are the libraries in Python that are designed to work with neural networks. Yes, and before we are going to start, I want to make a reservation right away that we are going to solve this project in Google Collab. We already mentioned in the first lecture on Python that this is a cloud environment from Google, which provides the opportunity to test machine learning projects directly in the browser. Why did we decide to choose Google Collab now? Because in order to solve this problem with neural networks, we need the TensorFlow library and the Keras module. And if you want to install them on your computer, often this can be very problematic. And there are a lot of errors with different versions, or compatibility with the graphic card and other errors. Whereas if you deal with Google Collab, you don't need to install anything. You just create a notebook and immediately start coding. Therefore, in principle, if you want, you can try downloading TensorFlow onto your computer. This can be done using the pip install TensorFlow command on the Anaconda command line in such black window, but with a very high probability you may have certain difficulties with further importing these modules into your project. And if such installation errors do occur, here you can see the most typical errors and how they can be solved. Therefore, for simplicity's sake, and in order to avoid these difficulties with installing TensorFlow on a local computer, we will show how to do this in a Google Colab. And here you certainly shouldn't have any problems. In addition, this cloud framework from Google gives you the opportunity to use more RAM than is available on your computer. Okay, let's get started and let's create a new notebook in Google Colab. Now, in the very beginning, we need to import the libraries and modules we need. First, let's import all main libraries. We will need NumPy and Matplotlib to work with arrays and visualize our drawings. As we mentioned, TensorFlow and Keras are necessary to build neural networks. The Fashion MNIST dataset is already available in Keras because it is one of such popular datasets on which all data scientists learn neural networks. Next, we import the sequential model. This is a neural network model in which layers go one after another. Then we are going to import the dense type layer, which means that our layers will be fully interconnected. And finally, we will also import various utilities that will help translate our data into a format suitable for Keras. Alright, so since we have already imported the Fashion dataset in the beginning, we can now load the data into our project. As we said in previous lectures, in machine learning, our datasets will be divided into two parts, training and test samples. And each of these parts will contain part X, these are the images, and part Y, these are the answers to which class this or that image belongs to. They are also known as labels. Class names are not included in the dataset, so let's write them ourselves. Okay then, so what's next? Now we need to pre-process our data before creating a neural network. And before doing that, let's first see what our images look like. In these square brackets we insert the index from 0 to 59,999, because we have 60,000 images in the training set. Some images are easy enough to understand, and some are almost incomprehensible. On the side of the image, you can also see the pixel intensity values from 0 to 255. If the pixel is as dark as possible, it has a value of 0, and if it is as light as possible, it has a value of 255. So, having seen our images, now we are going to do data normalization. What does it mean? This means that in order to improve the optimization algorithms that are used in training neural networks, we divide the intensity of each pixel in the image by 255, so that the intensity now is in the range from 0 to 1. And we will do it both for the training set and test set. Let's check it. Great, now the pixel intensity is from 0 to 1, and it will be easier for neural networks to work with such values. By the way, we can depict several images on one screen at once. To do this, you need to write a few lines of code. We are going to show the first 25 images, 5 in each row, and we will also display the names of their classes below them. Looks fabulous, doesn't it? If you want, you can make the images in black and white. So that's great. We have prepared the data, and now we can begin to create a neural network. In neural networks, the main building block is the layer, and the main part of deep learning is combining simple layers. In Keras, just like in machine learning in general, neural networks are called models. And as we have already mentioned, we are going to use the sequential type of model, which means that our layers will go in sequence one by one. So let's create a sequential model. The first layer, which is indicated as flatten, converts the format of images from a two-dimensional array, where each image was an array of 28 by 28 pixels, into a one-dimensional array of 28 by 28. That is, now the image will enter the neuron as a string of 784 pixels. Next go the two dense layers. The first dense layer is the fully connected input layer. Here we have to decide how many neurons we will have in this layer. In fact, a lot of experiments have already been done on this dataset, and one of the most successful predictions was the input layer of 128 neurons. Although if you want you can make 512 or 800 neurons at your discretion. Next we write the activation function. In our case, for the main input layer, we specify the ReLU activation function. It showed good efficiency in such simple neural networks. And then the last layer is the dense output layer. It will have 10 neurons exactly as the number of our classes. The activation function will be the softmax function. This function enables us to return an array of 10 probability estimates, the sum of which is 1. Each node on neuron will contain an estimate that indicates the probability that the current image belongs to one of our 10 classes. Before training the model, you need to make some more minor settings. This is called Modal Compilation. When compiling the model, we specify the training parameters. As for optimizer, in our case we use the SGD, which stands for Stochastic Gradient Descent. This optimizer is very popular for solving problems of image recognition using neural networks. Alternatively, if you like, you can use the Adam optimizer. The error function is indicated by the loss parameter. In our model, instead of standard root mean squared deviation, we are going to use categorical cross entropy. This error function works well in classification problems when there are more than two classes. And the last parameter is the quality. We indicate accuracy, that is the proportion of correct answers. After the model is compiled, we can print its parameters using model summary function. In principle, everything is ready, all data is prepared, we created and compiled a neural network, now we can start its training. The training of neural networks is done just like in other machine learning tasks with the help of the fit function. And since we have a classification problem, which belongs to the supervised learning, we pass on to this function both the training sample, xtrain, and the answers or labels, ytrain. We must also specify the parameter, the number of epochs. As we mentioned before, one epoch is when our entire dataset passes through a neural network once. We indicate 10 epochs, which means that we are going to train our neural network 10 times on the entire dataset, that is on all 60,000 pictures. You may ask how many epochs are needed. The answer will vary depending on different datasets, but the basic principle is that the more diverse our dataset is, the more desirable it is to use more epochs. And also you should probably take into account the power of your computer. If you have a very large amount of data and they are all very different, then each epoch will take longer time. Therefore, for the simplicity reason, we will use only 10 epochs. You may use more epochs if you want, it will just take more time and the quality will probably not be significantly better. So we can see that our training has begun. Here comes the first epoch. At the end of the line of each epoch, the error function is indicated through the loss parameter and the accuracy of predictions. As we can see, while our neural network is being trained, that is with each subsequent epoch, the value of the error decreases, whereas the prediction accuracy increases. So the last epoch has ended, and this means that the training of our neural network is also completed. We see that the accuracy is slightly less than 90%. Well, for a neural network consisting of only two main layers, this quality is rather good. Let's now check what accuracy we would have on the test sample. Remember that for training we used 60,000 images from the training sample, and 10,000 images were in a test sample, and our neural networks didn't see them. Therefore, let's see what will be the prediction accuracy on these test images. As you can see, the quality of the prediction is slightly lower, but still quite high. So, congratulations to you, you have built and trained your very first neural network. Now, after completing the training, we can use our neural network to predict what is shown in the images. To do this, we use the predict method of our model. We will predict on the images from the training sample on which our model was trained. So we write xtrain in brackets. And now let's print what our model will predict. In the square brackets we put the index of the image. Let's start with the image with the index 0. So we can see 10 different values, each value representing the probability of our image belonging to each of our 10 classes. Each value at the end has a -8 or -9, which means that they are in the -9 degree. That is, after a 0 we have a few more zeros, and that is, the probability is close to 0. And only one value with a -1 degree. You see 9.90 something minus 1. This means 0.99 hundredths, that is very close to 1. And as you remember, in our case, number 1 represents 100% probability. Thus, our model with a probability of almost 100% predicts that this image corresponds to this class. In case it's difficult for you to find which of the values from our output is the maximum, we can use the argmax function from the NumPy library. It just gives the maximum value. And so we are given the maximum value with index 9. Now let's check and derive the correct answer from our labels. So our true answer for this image turned out to be the same as was predicted by our model. That means that our model is working. You can test with other images. Just replace the number in the index with any other number from our sample of 60,000 images. Let's test number 12. Okay, it tells us that this is a class with index 5. Let's look at the image. What is it? it's a sandal. Actually, if you do not want to look through the images each time, we can simply print the class name by inserting the corresponding image index. Alright, that's great. My congratulations to you once again. Hope your neural networks work just perfect. And now let's summarize what we have covered. We imported the entire dataset with images, divided them into training and test samples, then we optimized these images a little bit. After that, we created the architecture of our neural network, which in our case consisted of only 3 layers. Compiled the model, which means that we specified the training parameters, then we trained our neural network using our training sample, and finally tested it on our test sample. Now you can try to predict other images in the training and test samples. You can also adjust the model a little bit. For example, you can use another optimizer, let's say Adam, or change the number of epochs and so on. By the way, on the Kaggle website, there are various versions of other types of neural networks with different numbers of layers and different architectures for the Fashion MNIST project. Therefore, you can look and try to make another neural network for this dataset. I hope this lesson was useful and it contributed to a better understanding of what neural networks are, how to train and use them, particularly for image recognition. If you still have questions, leave your comments, and I look forward to seeing you inside our new lectures and courses.